In this lecture, I'm going to be explaining this paper, How does simsiam avoid collapse without negative samples, a unified understanding with self-supervised contrastive learning. This ICLR paper in 2022. But this one, which is a positive sample, is part A of this playlist on contrastive learning, which I've explained. So the idea is that to avoid collapse in self-supervised learning, a contrastive loss is widely used but often requires a large number of negative samples. Without negative samples, yet achieving competitive performance, recent work has attracted significant attention for providing a minimally simple simsiam method to avoid collapse. However, the reason for how it avoids collapse without negative samples, even the BYOL algorithm doesn't use negative samples. So it remains not fully clear, and investigation starts by revisiting the explanatory claims in the original simsiam. And after refuting their claims, we introduce vector decomposition for analyzing the collapse based on the gradient analysis of the L2 normalized representation vector. This yields a unified perspective on how negative samples in simsiam alleviate collapse. And such a unified perspective comes timely for understanding the recent progress in self-supervised learning. So our investigation starts with revisiting the explanatory claims in the original simsiam paper, notably two components, one of them stop gradients, the other one was predictor, are essential for the success of simsiam. The reason has been mainly attributed to stop gradients by hypothesizing that, so instead of backpropagation, we use stop gradient. We propose to decompose a representation vector into center and residual components. This decomposition facilitates understanding which gradient component is beneficial for avoiding collapse. Under this framework, we show that a basic Siamese architecture cannot prevent collapse, for which an extra gradient component needs to be introduced. But when simsiam interpreted as processing the optimization target with an inverse predictor, the analysis of its extra gradients show that its center vector helps prevent collapse via the decentering effect, and its residual vector achieves dimensional decorrelation, which also alleviates collapse. But a single bias layer is sufficient to prevent collapse. We find that the extra gradient caused by negative samples in info and CE also achieves decentering and decorrelation in the same manner, and contributes to a unified understanding of various framework in self-supervised learning, which also inspires the investigation of hardness awareness from the inter-anchor perspective for further bridging the gap between contrastive learning and non-contrastive learning, such as simsiam and BYOL, in the context of self-supervised learning. And then simplifying the predictor for more explainer simsiam, we show that just a single bias layer is sufficient for preventing collapse, either full collapse or just a dimensional subspace collapse. We call it dimensional collapse. And for L2 normalized vector and optimization goals, self-supervised learning trains an encoder for learning discriminative representation, and to avoid scale ambiguity, the vectors are normalized before calculating this mean squared error. But collapse is SSL and a solution of simsiam, because Siamese architecture causes the collapse, and F always outputs a constant regardless of the input variance. Without using negative samples, simsiam involves a collapse problem by a predictor and a stop gradient based on which the encoder is optimized. So we have a symmetric loss. And here, this is a stop gradient, this is a stop gradient. Interpreting gradient, and so the hypothesis that the stop gradient is an implementation of alternating between the optimization of two sub-problems. Specifically, with the loss considered like this, the optimization can be solved by alternating between two different minimization problems. And this problem is formulated independent of the predictor, for which they believe that the usage of predictor is related to approximating EOE, of filling the gap of ignoring expectation in a sub-problem. So this is the architecture of simsiam. It's very similar to BYOL, and we can either use moving average like this or mirror simsiam. We divide the framework into two sub-problems with different paths and term them gradient path and sub-gradient paths. For simsiam, only the submodel of the gradient path also includes the predictor. The point that the reasoning flaw lies in the reverse of gradient path and stop gradient path. But does predictor fill the gap to approximate EOA? This paper points out that in practice it would be unrealistic to actually compute the expectation, but it may be possible for a neural network to learn to predict the expectation while the sampling of tau is implicitly distributed across multiple epochs. If implicitly sampling across multiple epochs is beneficial, explicitly sampling sufficient large N augmentations in a batch with the latest model would be more beneficial. And the difference between that naive Siamese and simsiam is huge, is that in whether the gradient in backward propagation flow through a predictor. However, we show that this propagation helps avoid collapse only when the predictor is not included in the SGP path. With H being trained, we optimize the encoder through replacing the Z with P. But clearly, how simsiam avoids collapse lies in its asymmetric architecture, one path with H and the other without H. Under this asymmetric architecture, the role of a stop gradient is to only allow the path with predictor to be optimized with the encoder output as a target. In other words, the simsiam avoids collapse by excluding mirror simsiam, which has a loss, where a stop gradient is put on the input. But we interpret H as function mapping from Z to P and introduce a conceptual inverse mapping. Simsiam, we can consider it with symmetric predictor, which leads to collapse. So we propose a conceptual inverse predictor, and if you see that it remains yet unknown whether such an inverse predictor is experimentally trainable. So we do vector decomposition to understand this collapse. And we decompose it into two parts, which is the center part and the residual vector respectively. And the center vector is defined as the average of Z over the whole representation space. However, we approximate it with all vectors in current mini-batch. A naive Siamese is well expected to collapse since the loss is designed to minimize the distance between positive samples. for which a constant constitutes an optimal solution to minimize such loss. So there is like a competition between that center and residual that I said. Similarly, the ratio of R in Z is M sub R. When collapse happens, all vectors are close to the center, and M sub O approaches 1, M sub R approaches 0, which is not desirable for self-supervised learning. A desirable case would be a relatively small M sub O and a relatively large M sub R. So the derived negative gradient is like where the gradient component is the dummy term, because the loss is a constant having 0 gradient on the encoder. So one conjecture is that the gradient component of your center of your O sub Z is expected to update the encoder to boost the center vector and increasing M sub O, while the gradient component is expected to behave the opposite. And we use extra gradient component for alleviating collapse. So it is challenging to derive the gradient and the encoder output in simsiam due to nonlinear multilayer perceptual module in H. The negative gradient on PA for simsiam, the predictor one, can be derived like this, that which is equal to Z sub E, and G here indicates the extra gradient component. But how this O alleviates collapse in simsiam? It is used to denote the center vector of P to differentiate from the above introduced O sub Z for denoting that of Z. So with the conjecture 1 that I explained, it is well expected that O sub E helps prevent collapse if that contains negative O sub P, because the analyzed vector is P sub A. But how O sub E causes collapse in mirror simsiam? The collapse occurs in mirror simsiam, which can also be explained by analyzing its O sub E. And you see, when you increase your temperature, you have a different parameters. We conjecture that, and of course dimensional relation helps prevent collapse. We conjecture that dimensional decorrelation increases M sub R for preventing collapse. This dimensional decorrelation. And info NC is a default choice in multiple seminal contrastive networks. The derived negative gradient is proportional to this term, and you see how closely info NC is related to these and could be useful for analysis. And you see the influence of various gradient components on M sub R and M sub O. But we can unify simsiam with info NC, because at first sight there is no conceptual similarity between simsiam and info NC, which I have explained both of them in different videos, and this is why the community is intrigued by the success of simsiam without negative samples. Through decomposing the G sub E into O sub E and R sub E, center and residual, we find that for both, their center plays the role of decentering and the residual behaves like decorrelation. So they just use the cosine similarity, but you can also use it symmetric. I mean P of B times ZA, as is done in the BYOL architecture.